Imagine you run a fraud detection system for a bank. Every night at midnight, you process the day's transactions, look for suspicious patterns, and flag fraud. But there's a problem: by the time you flag it, the fraudster has already transferred the money and disappeared. The batch approach finished the job 12 hours too late. This is the fundamental tension that stream processing resolves. In Chapter 10 we talked about batch processing, reading a bounded set of files, transforming them, writing output. Batch works beautifully when you can wait. But in reality, a lot of data is unbounded. It keeps arriving continuously, forever. Your users produced data yesterday, today, and they will continue to produce data tomorrow. The dataset is never complete. So what do? You could run your batch job more frequently, every hour, every minute, every second. But at some point you've abandoned the fixed time slice entirely. You're processing every event as it happens. That is the idea behind stream processing. In stream processing terminology, a record is called an event, a small, self-contained, immutable object with a timestamp, recording something that happened at a point in time. A user clicked a button. A sensor recorded a temperature. A payment was submitted. Each one is an event. Events flow from a producer, also called a publisher or sender, to one or more consumers, also called subscribers or recipients. In a file system, a file name identifies a set of related records. In a streaming system, related events are grouped into a topic or stream. Here's the key insight: instead of writing events to a file and processing them later, you want to be notified the moment a new event appears. That notification mechanism, that's where messaging systems come in. Next up, we'll look at two fundamentally different philosophies for delivering those notifications. Think of a traditional message broker like a post office with a twist. Once you pick up your letter, the post office shreds it. That's the mental model for AMQP and JMS-style messaging systems like RabbitMQ, ActiveMQ, HornetQ, TIBCO Enterprise Message Service, IBM MQ, and Azure Service Bus. Here's how they work. Producers send messages to the broker. The broker stores them in a queue. Consumers read from the queue and acknowledge each message. The moment a consumer acknowledges, the broker deletes the message. Gone forever. This design has real strengths. The broker handles durability. If a consumer crashes mid-processing without acknowledging, the broker redelivers to another consumer. Load balancing is built in. Message M1 goes to consumer A, M2 to consumer B, alternating the work. Fan-out is also supported. Multiple independent consumer groups can each receive all messages. But here's the counterintuitive part: this design also has a serious limitation. Because consuming is destructive, acknowledging a message causes deletion. You cannot reread old messages. If you add a new consumer to the system, it only receives messages sent after it registered. All prior history is gone. There's another subtle problem with load balancing and redelivery combined: message ordering breaks down. Say consumer 2 crashes while processing message M3. The broker redelivers M3 to consumer 1, but consumer 1 has already moved on to M4 and M5. Consumer 1 now processes M4, then M3 redelivered, then M5. The order is wrong: M4 to M3, M5 instead of M2, M3, M4. The JMS and AMQP standards require brokers to preserve ordering, but the combination of load balancing plus redelivery makes that impossible. For independent messages, this is fine. For messages with causal dependencies, where order matters, this is a serious problem. So we have a trade-off. Traditional brokers are great for task queues with independent jobs, but they're not the right tool when you need durable, ordered, replayable event history. That's where partition logs come in. What if we combine the best of both worlds, the low-latency notification of messaging systems with the durable, replayable storage of databases? That question led LinkedIn engineers to build Apache Kafka in 2011. The insight is elegant: use an append-only log. A log is simply a sequence of records written to disk, one after another. A producer appends events to the end of the log. A consumer reads the log sequentially from an offset, a position number. Within each partition, every message has a monotonically increasing offset number. Here's the revolutionary difference from traditional brokers: consuming does not delete the message. Reading the log is a read-only operation. The log just sits there. Kafka retains messages on disk for days or even weeks. In practice, because a typical large hard drive holds 6 terabytes and writes at 150 megabytes per second, it takes about 11 hours to fill the drive at maximum write speed. Real deployments rarely hit that limit, so the log can buffer several days or even weeks of messages. Each consumer tracks its own offset, the position it has read up to. The broker only needs to periodically record these offsets, not acknowledge every single message. This dramatically reduces bookkeeping overhead and allows for much higher throughput, millions of messages per second by partitioning across multiple machines. For scalability, the log is partitioned. Different partitions can live on different machines. Ordering is guaranteed within a partition but not across partitions. A topic is a group of partitions that all carry messages of the same type. Now think about what this unlocks. A consumer can fall behind and catch up, it just hasn't advanced its offset. Multiple independent consumers can read the same log simultaneously without affecting each other. A new consumer added months later can replay from offset 0, processing the entire history. You can experiment with a new processing algorithm against production data without touching production services. Apache Kafka, Amazon Kinesis Streams, and Azure Event Hubs all implement this log-based model. This architecture decouples producers and consumers in time, and that changes everything about how you build data systems.